now. Session is being recorded. Good. Again, the video won't be available immediately afterwards, but it will be available in a couple hours afterwards, and you can go back and look at it at your leisure. So, going back to the chat. So we finished our discussion on waves, which is one part of the component of building Maxwell's equations, and now we're going through beginning our long slog through electro and magnetostatics, because after we build up waves, we have to build up the electric field and the magnetic field. And in order to talk about both those things, either of those things in any meaningful way, and I'm realizing it's about to get dark here, so we're going to turn on the light. There we go. All right. So if any of those things are to have meaning, we have to really start discussing Coulomb's law. So as you can see here, I've got the pointer. Yeah, this is Coulomb's law. We'll get the pencil and circle it here. Now, this is how it's commonly defined. It will be simple for calculations if you define it this way, though, as F equals K. You're going to have to forgive the pen here. Q squared over R squared. And I should rewrite that actually, because it's only Q squared in very certain specific. I was just looking at the dipole, so I got a little ahead of myself. But you can also write this as F. Oh, hold on, let me get the pen. As F equals K Q1 Q2 over R squared. Okay, everyone sees that I've written this on the thing. This is all streaming well. So you shouldn't just be seeing me. You should be seeing the Coulomb's law slide. So with that being said, you might be looking at yourself going, this is much cleaner than this, right? You got all this crap going on here. But what makes this important is this little quantity epsilon naught here. This epsilon naught, this constant, will play a big role in defining our overall theory. So we want to be aware of it, we want to know its value, but for most of the electrostatic problems you're doing, you're going to want to use this value of K. It makes things cleaner and easier to calculate. It says it's 8.9 times 10 to the 9th newtons meters squared over Coulomb squared, but a lot of times people will just write 9 times 10 to the 9th, and you can see why this is a little cleaner and easier to remember. Okay, but while we're using this equation of Coulomb's law, it's important to note the physical quantities and some of these units we've talked about. Newtons and meters are from Physics 1, but coulombs, this is a new unit and is associated with what we talked about last week, which is charge, right? So we have charged particles like so here. Now I'm going to erase the stuff. I'm going to clear the tablet, but for those of you who just joined, please keep in mind this is being recorded, so you'll be able to go back and peruse at your leisure. There's no reason to rush to write anything down, or to really write anything down at all, because you can hear it all, the slides, the doodles, the voice, the comments. It all should be there. I hope it's all there. Anyhow, so I'm going to clear this because I want this to be a little clear. Now you'll notice you have two positive charges here. So charge is an intrinsic quantity a lot like mass. Now, we talked about this last week when we met, but or before the pandemic, a pre-pandemic fact, just before we stopped lectures. But and if you remember, we talked about interactions between charges. So we saw here that it's taking away my pencil. We saw here, for instance, that if the charges are like, right, or opposite, there's two types of charges, unlike for, say, gravity or mass. There's no such thing as negative mass. I remember we talked about that. And we can have basically three scenarios. We can have like charges and opposite charges. Now, opposite charges will always attract each other. Okay, and like charges will always repel. So quick question, what are these two charges are both positive? Will these two charges attract or repel each other? See if I can get one response via the text. I'm hopeful.
The two positives would repel, no?
Yes, good, good. That's what I'm looking for. That's a good way to just chime in too, as long as you, it's okay to unmute yourself if you want to chime in, Lewis, that was good. Anyone can do it, and then just be sure, we just don't want all the background noise going through. So chime in or put the thing in the text, like I said, whichever way you're comfortable doing it. So yeah, so that's charge in a sense. And we talked about a bit, we saw previously, we witnessed that different objects can be charged and react differently. And I think we saw the video on how water reacted to charge. Fortunately, teaching this way, I think I may have a shortage of cool videos to share the screen with. But hopefully after spring break is when I will figure out how to stream videos in a way that makes sense and incorporate it into Blackboard Ultra. Right now, I'm just figuring out how to use everything. You guys should be lucky. Earlier today, I didn't figure out how to hear the students talking, so I finally figured out which setting to toggle. So, you know, progress. But I will remind you when we talked about charge that we had these 3 types of charge. Oh, no! The pencil has gone mad. We had these 3 types of charge, which were the conductors, the semiconductors, and the superconductors. And fundamentally, these just describe how easy it is charge to get from one atomic state to another. Because when charge can flow or move through those states, it can create current. And we'll come back to current a bit later. For now, we want to stick to Coulomb's law and how charges interact with each other. Okay, so let's move on from the Coulomb's law expression. And see, they have this here. So hopefully that made sense. It's just the same thing we talked about. But what we want to discuss now is how charges can add and how charges will affect each other and how charge flows. All right, because it's experiments have shown that charge, and we'll actually talk about one that's really cool when we talk about magnetism, because you can actually use the methods of the equations in this class to prove that the charge carriers in metals has to be the electron and not the proton. But unfortunately, the way things were, original charges were sort of described by Ben Franklin of what was positively charged and what was negatively charged, we're sort of stuck with a convention that ended up being the opposite of what we thought. But one thing you can see here that I want to point out is that if multiple electrostatic forces do act on a particle, the net force is the vector sum. This is just sort of, it's similar to that idea of superposition, right? If you have multiple gravitational forces, they all add together, all right? And the shell theories will be our guiding principle of electromagnetism. So shell theory 1, a charged particle outside a shell with charge uniform distributed on its surface is attracted or repelled as if all the charge were concentrated at a particle at its center. I know what you're all thinking. Professor Toland, we can read that. Thank you very much. You are very welcome. I just do what I can. But I want to read it so that we can talk about what each of those things look like and means. So, when we're here, what we're saying is that if we look at a surface, right? So some sort of spherical surface and this little point charge. This is our shell. You'll notice all the charges, for instance, here would have to be on the outside of the conductor. They would not be in the surface. We're actually going to be able to prove that the electric field and thus the charge inside a conductive material must be 0, but we don't want to get too ahead of ourselves. This is, like I told you, this is an exciting class. There's a lot of exciting stuff to prove. And I don't know, I'm sorry you have to deal with the ice cream truck, but the neighborhood children, well, they may or may not be happy. I don't know if their parents will let them outside. But basically what this says is that here's our charged particle, right? It's outside of this shell. I need to keep toggling between the pointer and the pencil, between this shell. So I put all these positive charges out here. So basically what that statement says is that you can look at an equivalent situation in which you have the same particle acting at a charge that's at the center, so at the center of the circle, where the charge here, Q total, of this point is equal to the charge around the shell. So let me do that. So total of this one point is equal to all of these surface charges acting in the middle of the sphere. Basically, what this first shell theory says is that these two pictures are equivalent. Okay? Now, shell theory 2, a charged particle inside a shell with charge uniformly distributed on its surface has no net force acting on it due to the shell. Right now, we have to accept this. This is what I just said. So that means that a particle in here would feel no force from these charges. And we can actually use Gauss's law, which is chapter 23. We're going to use Gauss's law, which is one of our first big equations of the semester, big equations. And we're actually going to be able to prove that really simply, and it's pretty cool, but we won't be able to do it quite yet. We're just going to have to take it as part of our shell structure. So let's look. Oh. Yeah, Anthony? Question? Sure. So the shell theory here, and I think it was hard, Anthony, because of the toggling between the pen and the pointer, so I apologize about that. I don't think even in Zoom will let you do both at the same time. Okay, so the shell theory is this idea that imagine that you have this shell, this conductive shell where charged particles live on the surface. So as you can see, I'm moving around. These are all pluses. I forgot to cross this one, but I hope you get the idea here. All right? And you have a charged particle outside. So these particles can have a force between them. Okay? And so essentially what happens with the first shell model is that we can say that this picture here is equivalent to if we took all of these charges on the surface, and you'll notice it's a spherical shell because that symmetry is crucial. If it has the symmetry of a spherical shell, we can crunch it down to one point, right? Where QT, the charge total of this point, is equal to all of the charges here in this shell. Okay? And basically what we can say is that these two are the same. Now, the second shell theory states that there's no electric field on a particle inside here. It has no net force acting on it due to the shell. Okay? So that's what these two shell theories say. So I hope that makes a little more sense. But if not, you can hear both the initial part, because remember this is being recorded. You can go back and play the initial part and the repeat, and hopefully that makes sense. And I want to remind all of you, I have Skype office hours. You can look up the following email address on Skype, my address for LaGuardia, jtorn@agcc.cuny.edu. And I just put it in the thing. If you click on that in Skype, you should be able to get my my Skype account, and which is how I'll be doing office hours and things like that. So, so let's take a look at this checkpoint. We don't do as many of these as I do in Physics 1, but I try to pick the ones I like. So the figure here shows two protons, right? Proton 1 and proton 2, and one electron on an axis. So on the central proton, what is the direction of A, the force due to the electron, B, the force due to the other proton, and C, the net force? Okay, so we can look at this, and it's important to note one basic thing. So the one thing you haven't been told here is that, for this checkpoint, is that the charge of an electron, or I'm going to do it here, that the charge of an electron is equal to the charge of a proton. Okay? Their masses are very different, but their charges are equal, or at least the magnitude of their charges are equal. Let's do that. Yeah. Not perfect. And of course, this is the elementary charge, E equals 1.6 times 10 to the minus 19 coulombs. Okay? That's your elementary charge. Now, looking on the checkpoint here, let's look at the central proton. All right? So from the electron here, first ask yourself, will the force be on this proton? Is it going to be attracted to or repulsed by the electron? So what do you all think? Or a few of you at least. Again, we're looking at attracted. Good, they're opposite charges. So the proton will want to move towards the electron, right? So that's okay. And now let's change colors for the other one. So is the proton going to be attracted to or repelled from the other proton? Repel, good. So if we do that, we can see it's also moving in the same direction. You'll notice that it's a little counterintuitive, but it's additive. And I also want to point out that you need to look at the force on the object. All right? So there's two objects in each of these problems, and you'll notice that there is an action-reaction pair. But notice what the challenge problem says. It says, what is the direction of the force due to the electron on the central proton? So it says on the central proton, this one, right? We want to find the forces on this from the other stuff around it. If you make all those pairs, you'll get lost. There'll be arrows everywhere. It'll get rough. So we only care about this central proton, and that's all we're going to worry about. So, but the net forces are additive, so we know that the net force will be to which direction? Towards the electron or towards the proton? There's a new way of looking at it. I'm not going to ask you left or right. It's towards something. What's it towards? The electron or the proton? Towards the electron. Good, good. So, I think we've got that one. Now, you got it. Oh, you got it working? Good. I thought you were already in. Okay. So, remember, everything is recorded, so you can go back and look afterwards. But also keep in mind, it'll probably take a couple hours for the lecture to be available because the Blackboard has to process it. Now, so you can see here we have similar, more complex arrangements of charges, all right? So we have this first arrangement, which is very simple. We have this second arrangement, which is just like the checkpoint, right? And we have this third arrangement, which is a little more complicated and recalls to the fact, I call this setting up some problems in return to Physics 1, but you'll notice that, you know, this is going to be a little more difficult. And we have to remember that fundamentally what Coulomb's law is about forces, right? F equals K Q1 Q2 over R squared. No, that was a terrible line. Over R squared, right? This terrible thing is an R. But fundamentally, this is the magnitude of a force vector. And this gets a little interesting because unlike here, the Coulomb's law gives you the magnitude, right, the equation, but then you have to use your mind and you have to and look at and see if the forces are going to be repulsive or attractive based on the signs of the charge. And sometimes it will be important, particularly if we look at situation 3, where you're going to have a vector that is off axis, and then you will need to break things into x and y components, right? You're going to need to, you know, vector, you will be haunted by vector addition. And when you look at it here, you can see that if you look at Q1, it's being pushed away. That's pretty easy, right? And then here, you'll notice it's a little different than the checkpoint. Now you have a proton and a proton, but the electron is now in between, and you'll notice that it has these different vectors. And you'll notice that the distance is really going to matter here. The force between Q3, if you will, the electron, and Q2, whatchamacallit, let me see here, 3/4 R. This should be, so 1, 2 should be smaller, right? 1, 3 is there, or I got mixed up here. So looking at the forces on Q1. So 1, 3, you'll notice the distance is much smaller, and that's a much bigger force than the repulsive force from Q2 all the way over here. I just made the mistake I told you all not to do, right? I looked at Q3 and started doing things in terms of Q3, and that's not what the problem said. So you can see it's kind of easy to make that mistake. Don't do it. So this arrangement is, you can see here how that works, right? Now you'll notice here, Q14 is a two-dimensional force. It'll have this angle theta. So in order to find the forces, or to find the net force, you will have to take the x and y components, just like I said before. So take a look at that for a second. Are there any questions on how these three situations are interpreted into these net vectors on our Q1 particles? You'll notice particle Q1 is the analysis particle in each example, here, here, and here, and that we add Q2, we have a Q3 here, and we're just calling it Q4 there. All right, but F12, for example, is the same in all. So each one has a Q1 and a Q2, and then we're adding different scenarios in the two drawings. Okay? I keep looking at the chat like people are there, but I realize that I should be looking at the, like I said, it'll get better. So, all right, let us continue. So we want to look at how, wait, did I miss something? I should have. Okay, so charge is quantized. So I got the slides backwards when I wrote them. Okay, or when I modified everything. So you're going to sort of see some of the things I put in there. So charge is quantized. Now, what does quantized mean? That's actually a very interesting point and idea. So quantized is, it actually goes beyond just the regular, than the scope of this class. So what I mean by that is one of the fundamental arguments today between quantum physics and general relativity can really be sort of boiled down to, is the universe quantized or is it continuous? So if you don't know what quantized means, if you do the either or there, you might be able to see or get that quantized is discrete, meaning non-continuous. So I have, if I were to give you, one of the examples I usually like to do with this is if I were to offer you all a jump in your fortune in American currency, a quantum leap, if you will, I would have to give you a penny. Oh, yes. Who asked the question? I didn't. It just went away. I'll raise my hand. Hand raised. Oh. Okay. What was the question? Keep that hand raised. You don't have to double click it. Otherwise I can't see it. Or was it a mistake? I wasn't going to keep going. Okay. I'm talking. It's not muted. It's not going on. If you can't hear me, Mustafa, is anyone else? Can anyone else hear me? Mustafa can't hear me. Okay. So I think you might want to. Mustafa, you might want to check out and go back. Oh, okay. That was a okay. All right. I think. Okay. So it was just a misunderstanding. Okay. All right. Just let it go. Okay. Thank you. There we go. So by discrete, a penny would be a discrete amount in your American fortune. What I mean by that is I can only give you money physically. Jesus Christ. That's on my end. All right. That was weird. That was a fire alarm. So to get to to what I was talking about, Jesus, and to really get back to it, I can only give you money in American dollars in terms of pennies, right? I can't give you a half a penny. I can't give you 3/4 of a penny or 9/10 of a penny, even though gas stations like to pretend they can. So any amount of physical money can be broken down into the penny in American dollars. So another way to say that, or to say that in a more physics way, is that any amount of money you can have is always divisible by 1 penny. There's always an integer number of pennies that represents any amount of money you can physically exchange. Charge works the same way. And what that means is that there's like the electron and the proton have a fundamental charge value. And you can have charge values that have integer multiples of protons and electrons. But for instance, you will never find an object that's charged with a charge and a half of a proton charge, or 3/4. There are things called quarks. That's way beyond the scope of the course. And they've also never been the theory behind them is very strong, and there's experimental evidence for their existence, but they've never been directly observed. So we're not going to worry too much about it. But you can see that all charged objects have to be some integer multiple, that is 1, 2, 3, you get the idea, times this elementary charge value. And that elementary charge value, I approximated it before, but 1.602 times 10 to the minus 19th coulombs is the fundamental charge, or what we call the quantized charge. And again, to look at this idea of quantization, it just means that it can only come in these packets. 1, 2, 3, 4. It can't be continuous. There can't be like 1.1, 2, 3, 4, 5. Another way to look at this, if you want to be mathematical about it, this might help some of you, it may confuse others, is continuity is like the real number line, where in between every number there's an infinite number of numbers, and a quantized system is like the integers, 1, 2, 3. There's no integer between 1 and 2, right? It's just 1, then 2, then 3. Okay, so it's a concept that is subtly difficult, and then it becomes very difficult. But when you really start applying it, so my example was absolutely. But when I say quantization here, I'm talking about the charge particularly. When I was talking about money, so a object or set of objects is quantized, right? So money is quantized by the penny. This is the quantum unit of American money, the penny, which I think you can see in my hand here. When we say that the charge is quantized, it means it comes in multiples of this electric charge here. Okay, so any charged object, its total charge must be divisible by this number. Okay, that's what I mean by quantization. Yes, Jesus. Yes, exactly like that. Whole numbers in the number line. Yeah. And also, if you have a question, feel free to put your microphone on for the question too, everybody. If you want to do that, that's fine. I can hear you all now. So you just have to turn it back off afterwards. That's the part you got to double click on. So does that make sense? Again, it comes in individual parts. So you'll notice the electron has a charge of minus E. The proton has a charge of plus E. If you go and look at all the atoms, they have a set number of protons and neutrons, and their charge can be described as multiples of those. The neutron, of course, has a charge of 0. Neutrons are very interesting. They allow for lots of stuff to happen. So let's now, because charge is quantized, we know that it has to move sort of, if you will, pebble by pebble, like bit by bit. And one of the important things to see is that as we get bigger, we can find particles that have no charge at all, or a charge of, say, plus 10e or minus 6e, but you will not find something that has 3.57e of charge. It will have 3e, minus 3e, 4e, minus 4e, but this part is not allowed. All right? So once we understand that charge is quantized, it can be positive or negative, the next task we have to do, or the next thing we have to figure out, is how does charge flow? And I've already sort of, physics 2 is weird because historically we assume that positive charges would be the charge carriers, meaning that that's what flows when there's an electric current. But experiments have shown us, and we teach, and so now we teach from as if we just got the answer and always knew it was correct, that the negative charge carriers, electrons, are the charge carriers. And if you've taken some chemistry, that should make a little bit of sense. As you'll notice that bonds are what change in reactions, electric bonds. So let's look at this checkpoint. So negative charge would be, so the idea was, again, and again, this is Ben Franklin's fault. So an ion of negative charge is just electrons, electron current flow, and positive flow would be ion flow, right? So basically, Ben Franklin, based on some of the experiments we saw, based on rubbing and things like that, assigned what was positive and negative charge, and it just turned out that it got swapped, because when you start looking at it, he just got it wrong. So why do we stick to the current following positive flow? It just makes things easier. Everyone's used to it, and I guess they figure they'd rather make you suffer and get used to it than have everything make sense. There's some other, it makes a lot of calculations hard. What would the positive charge electron be called? Oh, so that's called the positron, and that is an antimatter particle. We're not ready to talk about that quite yet, but antimatter has occurred in high energy reactions, and we don't have a lot of it. But in normal matter, protons have positive charge and electrons have negative charge. And in normal systems, if you have a flow of positive charges, that would be due to ionized matter, not electrons. Whereas electrons can just be ionized and float and create a current. So we're going to learn about the Hall effect in about 4 weeks or 5 weeks. I don't even know anymore with this being online. And we'll actually be able to prove and make sense of this negative charge carrier business. But right now we will accept that the charge carriers are negative. We're not going to pretend they're positive, like Ben Franklin did, and we're going to sort of try to learn how charge flows. Okay? So initially, sphere A has a charge of minus 50 E, and charge B has a charge of plus 20 E. So one is negatively charged, one is positively charged. The spheres are made of conducting material and are identical in size. If the spheres touch, what is the resulting charge on sphere A? So that's an interesting question, and that requires us to know which charges flow. So, looking at this, we can, hold on, I'm trying to get get that out of my way. So let's take a look here at the circles, okay? So we have, oh, stupid pen. So we have two spheres, right? This one is minus 50 E. That's a terrible 5. And this one is plus 20 E, right? So if the charges touch, the negatives and the positives will attract. So you'll get those negatives will all want to go. Well, we're going to see. They should all, let me see if I get this right. So when they touch, like so, the negatives will be attracted to the positives and flow towards it, right? Until you deplete, the 20 charges. So at that point, you'd have minus 30 here, and you'd have 0. But that being said, charges, the movement of charges can be complicated. So if it's still seeing all this negative charge, the positives could be induced this way. And then you might get, the charges should spread through, because I'm thinking it is minus 15. But let me see, something, because this always gets, yeah, it is minus 15E. All right, because I was looking at it. There's still this induction problem, though. We still need to get there. No. Hold on. It's not listening to me. Or it listened too fast. That's what we're gonna. That's what we still have to look at. So minus 50. So at minus 50 E, basically what has to happen. The short answer to your question, Lewis, without getting bogged down in my own confusion, to be fair, is charge will equalize, right? Charge will want to split. So if you have plus 50 E here, or minus 50 there and plus 20, the charge, if these touch, the charge will redistribute and equalize, right? So basically, once the 20 here, once you get the 20 here to go over here, there's a negative 30 between each sphere, right? So once that cancels, because those will go right over and cancel out with that. So an intermediate, almost virtual step is that you have a point of 0 charge here, right? And then you have minus 30 here. But if they're touching, and this is the important part, if they're touching, that charge will distribute evenly through the spheres. So that way you'll have minus 15 and minus 15. And you'll still have minus 30. And then if you take the spheres away, you have minus 15 here and minus 15 here. So the reason why it's minus 15, it's sort of in, well, then it gets harder. But basically what happens is you'll have one remain charged, one remain non-charged, and you could have, it might be hard to tell where it is if the charge is uneven. So if it were 29 instead of 30, you could say the total charge would be you'd probably say one would have negative 15, one would have negative 19, for instance, or 13. But it wouldn't be, or 14, I guess it would be, but it wouldn't be both, right? You couldn't tell which one is which. The trick here is that two things happen, okay? One, let me get this thing up. One is that the charges equalize, right? All those extra electrons run to those charged particles. But keep in mind it's still charged, and what I was telling you about before is true. Charge separates and goes everywhere, all right? It doesn't clump. So even though you have these 30 charges, it's going to still go over here because positives will be induced until it's even. So I want to write down what that looks like. Yeah, unless it's, but remember, it's got to be a whole integer. We don't have these half integers. So in reality, one might be stuck going back and forth, and that would make an interesting bond. Hold on, Jesus. I want to go over this a little quickly because I think I've got a good explanation here. And this is a hard thing to get. So think about it this way. So at first, we have our more negatives, and negatives are the charge carriers, right? So all the negatives here are repelling each other, right? So they all want to run over to this 20. Now there comes a point where our intuition almost makes us think, oh, okay, well I've neutralized the 20, and so it should be minus 30. That's where the slides where I clicked forward and back and couldn't go. So that almost seems like it could be the answer, but we're forgetting something. Charges don't just stay here, right? So the charges, the negative charges, would still rather go to a neutral area than stay here. They're still going to be repelled, so if these are touching, charge is still going to go towards the sphere, B here, right? Call that sphere B. So even though it's neutralized at this point, the negatives are still repelling from each other on this sphere. Okay? And then the question is, like, when does it reach equilibrium? Like, when does it stop transferring? Well, it stops transferring when this sphere B is no longer the most desirable place to go. And so let's take a look at that. We'll make another sphere and another sphere. Now when we reach minus 15, okay, now when we reach minus 15, even though they're repulsive here, they're repulsed from here too. There's no place to go, so they can sit happy. Okay? So that's why the charge behaves the way it does. And I think Carl's point is well taken. It's so that he says so the charge that's dominant gets split between the material, like with -50, then the difference divided. This is one of those situations where I like thinking of it more in terms of the charge moving throughout the surface evenly, right? That's just what happens. Because if you had more positive charge than negative charge, I'm not sure those positives. I think what's going to happen is it's going to look as if the positive charges are moving. Let's take a look at it. Let's flip the signs and see what happens. All right. And I think I'll show you where I might have some issue with the dominant charge flowing business. Because even if we have, oh darn it, if we have here, right, say we had +50, and here we had -20. Oh, this is interesting now, right? Because it's tempting for me to say, oh, well, now the positive charges moves, and we could do that. But that's not really what's going on. What's going on here is that these negative charges will go over here, because it's always electrons that move. They will neutralize out. This will still be +30, right? But now what you have over here is it's 0, but you have all the negatives want to jump over here, and all the positives on this side. So charge gets induced and separated, okay? That's a really key point that you're going to have to get used to and apply. Now, because that happens, more electric charges jump over to our 30 + 30 charge, right? And so we still have negative charge going over until there's no preferred place. And that happens, and again, I'm switching the signs here, so don't get too confused. I'm switching the signs, and then eventually we get 15 and 15. So it's always the negative charge that's going to flow from one to the other, all right? But here we have +15 and +15 if we split the signs, and with the way it's given, we have that -15, okay? We're going to see that a lot more, so I want to go on a little bit, but I want to talk about it again in terms of another example that this slide was supposed to go later. So it's the same slide, but the whole thing is a little more manageable. All right. So what I mean by that is we can actually see and have better pictures instead of, well, my poorly drawn ones. And let me see. What did you want me to repeat, Anthony? Because if you want me to repeat what we did, we're sort of going to, but with this example. It's the same thing as the checkpoint. It's just a little more streamlined. So if we look here, we have two identical electrically isolated conducting spheres. All right? A and B are separated by some distance A that is large compared to the spheres. That just means that they're not so close that the spherical properties matter that much. The dominant charge is the negative. Well, in the checkpoint, yeah. Well, that's why I don't like the dominant charge language. Yeah. Because again, it's the charges equal, whatever they are, and we'll see it here too. Let's take a look and see if this makes more sense of it. And if it doesn't, we can have a conversation about it. So right. So sphere A has a positive charge of +Q. Again, this will just be some number. So we're just going to assume it's some integer number of the elementary charge. And B is electrically neutral. Okay? Now, there is no electrostatic force between the spheres. The large separation means there's no induced charge. So, okay. So now it's going to ask us to start. Does it ask a question here? All right. So basically what happens is it wants to look at, just like the checkpoint did, what happens when these two spheres are now connected. When the two spheres are now connected, now there is force and charge can be induced. And you'll notice that it's not here's what doesn't happen. You'll notice that positive charge does not transfer to Q, to this sphere B up here. What happens is negative charge that's free to move rushes towards the more positive Q charge until they are equal. All right? So even though it looks like you can describe it that way, what is physically happening is those electrons rush over and charge the spheres. I want to make a drawing down here to sort of illustrate what exactly happens in these spheres. So let me do that. Yes, good. Yes, equilibrium is usually always our ending point. So let's call this B, right? Now B is electrically neutral, but that doesn't mean charges don't exist. It just means that we have charges sort of everywhere, right? And we have negative charges in here and positive charges, but you'll notice if you counted them up, you get 0. So it's negatively charged. Now, sphere A has lots and lots and lots of positive charges. But don't think that doesn't mean that negative charges don't exist here and there, but all the charges are overwhelmingly positive. What that means is basically there's that many more positives than negatives. You can think of it as a population thing. So I think looking at it like this makes it easier because you can see how the charge is going to flow, and I think seeing that there is both types of charges present in each of the spheres makes the analogy clear. Now look what happens when I watch it, when I connect them now. When I connect them, the negative charges are already pretty happy. There's so many positive charges, but the positive charges, remember, like repels, say, oh, I don't like this, but they can't really move anywhere because atomic forces are stronger. But what can happen is over here is these negatives, there's a second part, these negatives go, oh, wait a minute, there's a lot more positive going over here. So what happens is, I gotta erase it, is that remember that sea of particles, or that sea of charges, rearranged to look like this now. So now we see the negatives lining up here, and the positives lining up here, instead of that mishmash of them floating around. And you'll notice you still have a neutral sphere, but now all these negatives see this positive, this largely positive charge, and they all just want to run right the hell over there. You know, just pop in, and they go, but eventually, right, the charges settle out, and you have positive Q over 2 and positive Q over 2. Now, when that happens, when the charge here is Q over 2, and the charge here is Q over 2, right? Ignore the stuff inside. When that happens, now the negative charges, it's like, ooh, it's positive Q over 2, positive Q over 2. I'm okay. I'm not going to move. And that's what happens. I don't know where those, oh, God. Hold on. I'm going to clear this before that gets out of control. Okay, that's the pen has decided to have its own life. I'm not going to allow that. But basically, when you have here is all those negative electrons now have gone over here, as this shows. But now think about I have to do this. Now think about an electron here. It's just happy being here. It's not getting much by being over here. So that's when that equilibrium is. That's when the equilibrium is managed, and that's when you have it. Jesus, your hand's been up for a while, so I want to be sure we get to your question. I'll lower your hand, but you can activate your microphone if you want.
Oh, can you hear me?
Yeah.
And when there's a plus Q2 and a plus D, that means that they're in an equilibrium state.
They're in a what?
They're in an equilibrium state, right?
The equilibrium with C, right.
So if it was A, B showing, that's where the that's not the track.
Right. That's not attraction. Attraction can't happen till B. Very good, until they're actually touching. Yeah.
Awesome. All right. Thank you.
So now what happens in D is the charge is grounded. Now remember, the initial part of this problem is that unless these two are touching here, right? How do we see what you write? It should be showing up. Can you see my pointer right now? Because what I write should be pointing up on the PowerPoint. Okay. Let me write something right now. So this here is ground. Can you see it? It's coming up. It'll be on the video. I can tell you that, Carl. It should be there. But others see it. So I don't know what setting is not letting you see it though, because other students do see it. But I'll try and figure it out for next time, and let me know if you still can't see it by the end of the night. And when you look at the downloaded video, that should have the writing on it too. So if it doesn't come up, I'm really sorry about that. I don't know how to fix that particular problem. So I'm deleting the ground part and going back to this. So when you ground something, you ground it to a low potential area. You shouldn't know what the word potential means yet. Don't worry about it. But it's a place basically all the negative charge wants to go. So when you ground this, right, basically negative charge from here, or negative charge from the ground, will rush towards the positively charged point until there's nowhere reason to go, and then it's all at zero. Then this whole thing remains zero, and this remains charged. So this is charged through induction, really. And if we were doing our normal labs, you'd actually do this in the laboratory with a fun thing. But what I'm hoping that you start to see, and I think there are good pictures of this in the book. Right, exactly. Physically, it means, that's right, Douglas. Electrons travel from the Earth to the sphere. Good. And then you get this charge up here by itself with this plus Q over 2. Getting the hang of charge transfer is difficult under normal circumstances. I imagine it'll be more difficult under these circumstances, but we want to understand that mechanism. Understanding that mechanism of what charges are doing will make these problems very clear. Much like a free body diagram made problems in Physics 1 very clear. As long as you can sort of get a feel for what's going on, it will be much easier to solve the problems and to analyze the theory. Okay. So with that being said, it's my voice is getting tired, and it's about 6:45. So how breaks are going to work is I will be around. I'll turn off my mic and video. I will answer questions on the text on the texting platform. But I'm gonna, I got to get some water or something, and I will not stop recording. Okay, so it'll only be one video per session, so I'm not going to do that to you and make you figure out which one's which through a bunch of different files. So we'll keep recording, but I'm going to turn my mic and camera off, and then that way you'll know when break is over. You'll see me back with the mic and camera on, and I'll start talking, and I should be cutting through to your things. So if you all want to talk to each other or whatnot, feel free. Okay, so it's 6:45 now. I wish I could get ginger tea, but I am homebound. I'm going to have to get some Amazon stuff. Okay, so I will be back around 10 to, no, not 10 to, about 6:55, and we'll get started again around 7, and we'll go to 8. Okay. All right. I'll see you all in a few minutes. So I will say I'm away.
Hello?
Wait, you can hear me now?
I can hear you.
What about?
Wait, what was going on? Wait, what? Hello?
Wait, but I thought the microphone stayed off the whole time. What? Also, should we tell the professor to turn down the sensitivity on his mic for a bit? Because the distortion is, oh man, it's killing my speakers.
Oh yeah, I can tell that the ear rape is going pretty bad,
Exactly, like it's killing me. Like I can barely hear what he's saying.
bro. It's not that bad still.
All right, I hear you. I'm doing the thing. Hold on. All right. That's my speaker volume. So my microphone volume. How the hell do I change that?
Go to what's it called? In settings in Windows, and it should show mic settings, something like that. Or type in mic setting. I think I'm not sure.
All right. How is everyone's? Is it better? Turn your speakers down a little bit. Is your that might be an issue. What's this? You're gonna clear that.
It's a little better. It's not so bad now.
Okay. Well, I gotta get the webcam. Yeah, I'm still figuring this out too. So, it's it's gonna be bad. Yeah, I think you just need to turn me down. That's probably how that has to go. The microphone's just the input. But I see that it goes. All right. So let me see. I think I finished everything here. That's a good place to start, but yeah. Okay. Oh, let's see what I missed in the chat. Oh, you see the Dalek in the background? Yeah, I don't have the, those of you that are missing it. Yeah, it's pretty big if you want to see the scale. That's me. I have to get the stuff and put it back on it, though. Whatchamacallit, it's packed away because I just moved here. Alright. Oh, okay. So Mustafa, you saw that lag was huge when people started really talking. Okay. I saw that. Oh, so I got 20 of you. I'll take the picture of the thing, the attendance, because that's a good time to. There we go. I can take the. They still want us to do web attendance. Why? I don't know. They just do. So I gotta do that. Yeah, I should probably put. Oh, that's right. I didn't put an avatar thing there. I guess we probably should. If we did Blackboard avatars, I could see everyone too, so I'd be able to put faces with names. Some of you I can, but we did go to distance learning very shortly. So. That's a good question. When I figure it out, I will let you know. I have no idea. Mustafa seems to have done it, so maybe he can educate us. Settings bottom right. That is definitely a after class time thing that I'll figure out. I'm not figuring it out right now. I will do nothing because I can't exit this session or jeopardize anything like that because I don't want a recording to disappear. That is my great fear at this point. As long as the recording stays intact, we will, we'll be good. All right, we'll get started in about 5 more minutes. I'm going to take a little walk again because now I have the opposite problem. Now that I'm sitting all the time giving these lectures, I need to walk around a little. So I'll be back in a couple minutes, and we'll get started promptly at 7. So I'm just going to mute these. I'm back. I miss the face-to-face too. It helps, but you know. I can tell you what I'm not going to miss, though, is not being able to eat at night, because after we end class, I have a sandwich in the fridge, and I get to go just get it and not worry about things closing on the way home. So, you know, you got to find the silver lining in the cloud. Okay. Are we ready? All right. So, okay. So I'm talking, so hopefully you can hear me. Yeah? Sharing audio, everyone? Yes? Okay, good. All right. So basically, this last slide is about conservation of charge, and what you're looking at is actually kind of fun. It's a particle accelerator track. So when you look at things like advanced high energy physics experiments, this is the kind of stuff you see. And basically, charge is conserved in physical systems. What I mean by that is that if you start with, it's a lot like energy. If you start with some amount of charge and something internal happens in the system, you don't lose overall the amount of charge in the system. This becomes really important when you talk about things like quantum physics, and especially quantum electrodynamics, which is the branch of physics that originally predicted the existence of antimatter. I talked about the positron earlier today. So this conservation of charge implied the symmetry of charge, and this guy, Paul Dirac, predicted it explicitly with his equation, and it's pretty cool. It was shown to be found and experimentally verified. So that's pretty cool stuff. But we really want to move on to electric fields. So let's go to share the files. So we want to stop sharing that one, and we will go to chapter 22. I had some problems switching files, so hopefully this will just go up. Okay. Yep, see, it's happening again. It's making me mad. So I'm going to go to, I should have done this during break, but I thought maybe I had somehow figured this out. But. So this file, we need to stop. We'll click this one. So I think what I'm going to do is I'm going to remove the offending files from now on. So now this is the only option. Electric fields. Can't go back now, can it? Yes, so Mustafa, so I'm recording the entire lecture, and no, just worry about what I have. No, don't worry about conservation. It's a fun thing to learn about, but don't kill yourself over it. But to Mustafa's point, again, I'm recording everything we do, and this entire recording, including slides, what I've written, and the chat questions are being recorded. So it'll take a couple hours to process, but by tomorrow morning, you should be able to access it. As long as I don't do something stupid like leave the session before I stop the recording. So yeah, so you should be able to play back everything as you want in any speed you want. So, okay. Yeah, so the homework, it's going to be a little like we talked about, Caesar. It's going to be the first test. The first test date is I'm going to probably, I have to figure out when that is. It'll probably be like right after spring break, and I'll have the first sets of homework due then. And I'm just going to have it due by exam rather than by week. I just want to give people flexibility, because one of the realities of distance learning or of a pandemic is, situations can get dire pretty quick, and you just might not have access. So I'm trying to give enough flexibility that that can happen. The only thing I can't offer flexibility over, and everyone's pretty much agreed on this, even though it sucks, is the tests. But I'm trying to give you enough notice so that you can be like, okay, the world can't collapse this day, and you have that 3-hour notice. So we'll I'll have more written instructions about that over the weekend and next week, as I'm hopefully feeling better and have enough energy to write that stuff. I was supposed to get a lot of that stuff done over the weekend and Monday, but I was out of commission pretty hard. So so hopefully that'll make sense. But now that we've talked about charge, I want to get back to this. We've defined what charge is as a physical quantity and what it looks like. We've talked about Coulomb's law. We can look at forces between charges. As I pointed out, I didn't point this out today, but I did before we went on our pandemic break, that the Coulomb's law looks like Newton's law. And if if you want to read these, we're not really going over the slide, but it's a good sort of blank slate to remind you that Coulomb's law, which we just saw, F equals K Q1 Q2. That's a better line, over R squared. Right? That's Coulomb's law. And with gravitation, we had F equals between two masses, big G, M1, M2 over R squared. And what you're actually going to find is that a lot of the problems are asked in a very similar manner between those two chapters. But what you're going to see is that a lot of the thinking, the abstraction is the same. It's just different physical quantities. But now that we have the physical quantity of charge down, we're ready to sort of become very abstract in our thinking. And we are going to introduce this idea of the electric field. So this begs the question, of course, what is the electric field? What is K? Remember, K is 9.9 times 10 to the 9. No, 9. I'm sorry, 9 times 10 to the 9th. It's that constant. We talked about it in the last chapter. If you look in your book and stuff, you'll see it everywhere. So here's the question about the electric field, and this is probably a good way to frame this. Okay. Oh, all right. So how does particle 1 know of the presence of particle 2? That is, since the particles do not touch, how can particle 1 push on particle 2? How can there be such an action at a distance? Now, action at a distance is one of those weird things that used to be very scary because it created all sorts of problems in and of its own. And with the idea of, can something, spooky action at a distance, yeah, that's the thing. So the idea was, well, how do we describe how is a charge aware of another charged particle before they touch? And this idea of the electric field solves this question by insisting that a set of charges produces an electric field that has values at all points. And so what you see here is an interaction of fields. And an interaction of fields is probably one of the least intuitive ideas you can think of, and it's one of the most fundamental, because what we actually find is that in quantum physics, the field is fundamental. So if you really want to tear reality down to its, back past coronavirus and molecules and DNA and down to even past the atomic structure, the way in which atoms interact in this universe is through through these field interactions with other fields. And even particles themselves are thought to be just localizations or clumping up of these fields. So it's really fascinating. It's terribly cool, but it's very hard to really grasp. One of the things I struggled with grasping this concept when I first learned it is that we're going to define the field as having a value everywhere in space. And that value means everywhere in space. That means that there's a value, in Alpha Centauri of the charged particle you have here, classically. Something that was interesting is that field is there, but the information in that field travels at the speed of light. So that's an interesting interesting thing that fields allow us to do, or other feature, is when physics gets more complicated, or when we find that our classical models break down, we can, well, they can only see us, they can only, well, the only thing that travels at the speed of light is light, right? Nothing else travels at that speed. But electric fields can travel, or it's not that the field travels at the speed of light. I think the better way to think of it, I think the correct way to think of it, is that the field is there, but it can only be perturbed at the speed of light, right? So it's, if you remember Estelle from the lab, you can think of that as the field, right? And then the wave moves those things up and down, the parts of the wave machine up and down in the field. Yes, it is similar to gravitational fields, although electromagnetic fields are far more better understood than gravitational fields. Gravitational fields are, well, they're complicated, they're tough, they're hard. Getting a handle on gravity is difficult. When you get to that level. So, yeah, no, gravity is definitely spookier, I think, for sure. But we can see here, I want to at least leave this up so when you're reviewing it, you can see that basically this, this paragraph is the discussion we just had. So I don't feel the need to read it, which is awesome, because reading off slides is even more boring here than the other thing, than in the classroom. But this is basically talking about field interactions. Yes, well, quantum entanglement is a little different. You could think of entanglement as interactions, as fields being within superpositions of each other, but in some ways it's a little more, it's a little different. But it's definitely sort of the first Lego to build that picture, definitely, absolutely. I think the closest this would come is like the superposition of quantum fields, but entanglement is about specifics, and it's like a second order process. And what I mean by that is you have the fields can be can interfere with each other, but now you have the particles, which are localizations. Now those are interfering. So it's like an interference within an interference. And I'm not a quantum field theory guy, so I like to pretend I am sometimes. So I'm very much reaching there. But I believe, from my understanding, that's how to look at entanglement in a field theoretic picture. But I could be wrong on that one. But certainly the electric field and learning about fields is how we build up most of our most sophisticated physics and our deepest understandings of reality. So I'm going to move on. Again, this is just reflecting our conversation, this slide, so not going to read it, and says exactly the same thing I did. One thing I want you to look at here, though, is how to start thinking of the electric field, all right? Now, I want to draw your attention. I'm just going to, wrong way. To this equation here, where we define the electric field. So you're going to notice that the force, the electric force, another way to write this is that the force is equal to Q times the electric field. I want you to note that we still have vector quantities here, so even though charge is a scalar, the electric field is not. And the electric field at any point is defined in terms of the force that would be exerted on a positive test charge Q placed there. So this is where we get back to this business of our test charges will be positive generally, not negative. And we keep them positive so that the math is easier. If we were going to be more realistic, we would definitely use an electron. But an electron, that's going to give us all sorts of minus signs, and we just never change the convention. So, but I want you to notice that we have this charge, we have the force between the test charge and this negative charge distribution. So I want you to see that, and I'll say that again. This is a charge distribution. This is the test charge, and that's the force on the test charge, right? It's attracted to the charge distribution. So going forward, if we now look at the electric field in the same way, we'll notice that the electric field acts symmetrically around the charge distribution, right? You can see it here. And you'll notice for the negative charge, these are called field lines. You're going to notice they all end on the negative charges. And that's one of those properties we're going to see of electric field lines, is that they start on positive charges and end on negative charges. So we're going to look at a physical system we will spend a lot of time on this semester. That is 2 parallel charged plates. It's going to have the special name of a parallel plate capacitor. So if you want to read forward to something. But the electric field lines, you'll notice we have positive charges that, unlike our previous charge distribution here, where you'll notice they're all coming in and ending on the negative charges. When we look at these positive charged walls, we're going to notice that the field starts from the positive charge. So when you're drawing field lines, and you will have a lab that deals with this still, is that field lines always start on positive charges and they end on negative charges. All right? So you can see that when you put your positive chest charge here, right, you can see that the force will repel from the charged plate. Now, you'll notice that when we look at the point charge as just a point, the electric field will push that positive test charge along the electric field line. All right? We're not looking at the field due to the test point charge, okay? We're only looking at the electric field due to the charge distribution here. And that's how you have to kind of look at it. And if you look at it on its side, it becomes, a little hard, because in the surface, it's going to go both ways. And that's going to give us some interesting factors of 2, I guess you could say, that we look at. But when we look at the electric field vector, we're always going to look at it at a point in the field. All right? So you got to be careful. And I want to slow down a little even here, because I can already feel myself going too fast. The field is something we can quantify, right? And we can draw these field lines. However, if we have a test charge, we're only interested in the electric field at that test charge, okay? So when we look here at this point, you'll notice that gives us the electric field only at the value of the test charge. So if you wanted to map the electric field of this charge distribution, you would have to be able to get this test charge and pick it up and move it different places. And then you'd get different values of your electric field. Okay? Does that make sense? We good here? Because I think it makes sense, but I can also very much understand how it can be confusing. No questions. So does anyone, maybe I'll give you a minute or two to think of questions you might have. Yeah, I'll stick around after class for a little bit. I'm gonna say after I go off, I can definitely be reached via my Skype if you want to do one-on-one questions, and that might just be easier. And I have the Skype question above, but I'll put it down at the end of class. Okay. So that is the central question, Lewis. If you read his question, Lewis just asked if F is a vector in the force, what is E? So E is the electric field. So F is the force from this charge on here, and E is just scaled by Q. Okay? If F vector is the force, right? So force is, so the way to look at this is we can see that there's forces, right? We can, what I mean by that is if I push you, you push me, it's intuitive. The question is, you can see these charges moving with forces, but they don't interact, they don't touch each other. So the reason to necessitate or invent E is to create a physical mechanism in which the charges can interact. So what we're saying is that the force is due to the charges in this electric field. I think that's fair, right? Because I'd say this is a chicken and the egg comment, because I'm tempted to sort of just jump in and say, right, that no, the force distribution tells you whether it repels or attracts. But what I just said, it's fair to say, well, wait a minute, doesn't the charge distribution produce the electric field. So I think what I might be more comfortable, because you can go, well, is it the electric field, is it the charges, is the electric field is the physical mechanism that allows that force to be acted. So in a sense, yes. If that did manage to confuse you more. Yeah. But again, I could see someone saying, well, the whole charge distribution sets up the field, which it does, but the field mediates that force. You know, it gives you that agency. Remember we talked about in physics 1, a force needs an agent. The agent is the electric field. I like that. Yeah. Okay. Okay. All right. Good. So this is more common. I like this one with the field lines here. If you can see this, you have positive, positive, and you'll notice that two positives charges, we know they'll repel, and you can see the electric field repelling. And so in this case, this actually goes to Lewis's question a little bit, right? Is if the field is created like this, and I put a test charge here, which is exactly what happens, all it can do is follow the field. And in this very real sense, yeah, it's because of the field, it just follows the field lines. You'll notice also something interesting. The field lines never cross, okay? They go up here and they're parallel, but they never cross each other, all right? It's sort of like Ghostbusters. Crossing the streams is bad. I realize that's an old movie. No one's seen it. And I can't see your eye rolls and groans. I'm sorry about that. So I might think that my 80s references are funnier than they actually are. Yeah, sort of like those visual magnetic field lines. Field lines are matter? No, they're not quite matter. They're just there. We can see them and measure them. We can see how matter reacts to them. But they're a property, they're something that's created by the charge distribution. It's actually really a deep question, Douglas. It touches on a lot of things that I'm the more I think about it, the more trouble I can get myself into. So I will stop. But field lines, right, are important for the interaction of matter and light. So in that sense, weird stuff can happen. But in this class, we can say they're not matter. They're just a property that emerges from the charge distribution. So what did you ask about symmetry, Jesus? You asked about symmetry. No. While Jesus is doing that reply, Lewis, it's very important to realize that the field is the medium by which the wave can travel. Right? So gravitational waves travel in a space-time, a 4D space-time. That's the medium by which they fluctuate, and that's what's fluctuating. Electromagnetic waves, for example, travel in an electromagnetic field with an E field and a B field, and that's what's oscillating as that propagates through space. Is the electric and magnetic field. So the way to think about it is, if you ask yourself, it's not that the field is the wave, it's what's oscillating from the wave. Okay? I hope that makes sense. I think it makes sense. Anyway. All right, good. So I want you to notice some things, though. You'll notice that the closer you get to the charges, the more densely packed these field lines are. So that means that the force is stronger, right? So you'll notice here, you can have like 3 field lines right next to each other, but if you go way out here, those same 3 field lines are very far apart. So it gives us the intuition, the way we draw the field, right, about the strength of the force, which is what it's supposed to do, because we should have a large force here near our positive charge, but then as we get farther away, the force should lessen, right? So again, and this star chart here, before we move on, I do want to reiterate that electric field lines, they always extend away and start on positive charges and end in negative charges, okay? So Let's go on. All right. So now you'll, if you recall, I want to do some writing. Now the magnitude of the, if we look at a charged particle, right, just one particle, we'll notice that the closer we are, the larger the field lines, right? So you have these long lines here, but you'll notice that I'm far closer to the positive charge than these points or than even these points still. All right. Now, I do want to draw something. You'll recall that from Coulomb's law, we have F equals K, where K is equal to 1 over 4 pi epsilon naught. You always want to keep that in mind, okay? K is equal to, or K times Q naught Q over R squared. Now, why do I write this like this? Because you'll remember we had another equation for force with the electric field. We could write that force is equal to Q naught E, right? Where Q naught is the test charge and Q is the charge distribution. Now, when we look here for a point charge, this becomes pretty easy now. We can see that F equals, from Coulomb's law, if we want to solve for the electric field, we can say that it's equal to the charge, Q, so that would be this charge right here, right? Not the test charge, times K, that's still there, over R squared. And that gives us this equation right here. Okay, that's how we get that. And you'll notice that our oh dear. You'll notice that our charge, the electric field lines, are behaving just like they did in the previous slide. Everything is starting on the positive charge and emitting away. And one thing you want to be aware of is if there is more than one particle, okay, in a if you have several point charges, say we added a bunch of them, the individual field lines may not cross, but if you have separate field lines, right, they may intersect and they'll behave like a wave. They'll they'll obey that position superposition principle, right? Just like we had with waves, if you remember, as one wave would come, they'd meet and add and then pass through each other and not lose information. That's what happens with fields. So, for instance, and what I mean by that is, say we now had a bunch of charges, right? There will be an electric field associated with this group of charges, and we'll look at our test charge is what we'll put to map the field, right? If we pick this charge up, I'm realizing how much I dislike switching between the pencil and this. If we pick this up and put it different places, we'll get different values of the electric field, just like we could here, right? These are all different locations we can put our point charge. We'll get different values of the electric field. All right? So, going on, we have another checkpoint. So, in the figure here shows a proton and electron, E, on the axis, on an x-axis. So we have our electron, we've got our proton. So what is the direction of the electric field due to the electron at A, point S, and B, point R? What is the direction of the net electric field at point R and S? So that's pretty interesting, right? So let me look up here. So I want you to play around a little with it, and I want to just look at each point first, right? So the first thing is we want to know what the electric field is from the electron. So in that case, we have just the electron, and we forget the proton, right? The proton's not in here. We can put our point R and point S. So the question I have for you is, which way, let me make another point here. I know they're not perfect, but are the field lines going to go into the electron? Remember, well, first of all, is the electron negatively or positively charged? That's the first question. Right? That's an easy one. It's getting a few negatives. Good. So remember, if it's not clear, electrons are negatively charged and protons are positively charged. The question, Lewis, was, is the electron negatively charged or positively charged? So, and the answer, right, I just kind of gave it away, was electrons are always negatively charged. Yeah, good, right? So, so yes, no, it's negative. Don't want to cause, that's where I don't want to cause confusion. But remember, but now we get to sort of the challenging part. Do you remember, do field lines go into positive charges or away from positive charge? Or, I'm sorry, let me rephrase that. Do field lines go into negative charges or away from negative charges? So is the field line going to go in like this? Is it going to be the blue line? Or is it going to be the red line that I'm going to draw here? Which one of those is correct? Away, good. Right. Well, so we have away, we have into. So remember, field lines always start on positives and end in negatives. So when we go back to do this, it's the blue line. It's the blue line that's going to be correct. And so from point S and point R, it should be going into the electron. Okay? It's always all charges. It's a good rule. So Lewis just asked if it starts at positives and ends at negatives. It's always away. It's just always away. It's always, field lines always go away from positive charges and towards negative charges. That's just the convention we have. So let's actually look at it away. You'll notice if we go back here, this is a positive charge. The field lines all start on the charge, if you will, and go away from it, right? Oh, hold on, you can't see that. Dumb thing. You can see them all going away. Now, if we were to make this a negative, if we look at a negative charge, which we had earlier in the chapter, I want to point out that they all go in. See, this is a good slide of them all going in. Do you see what is it clear now what I mean about starting and ending on them? You'll notice that these here, we have them ending on the negative charge, and then we see here that if we just have only positive charge with the point charge, they're all emanating, right? So now we have the black lines represent in the, which black lines? I'm confused. This one? Oh, these are negative charges. That's just saying they're negative charges. Yeah, the negative, that's just saying it's a negative charge. It's 1 negative, 2 negative, 3 negative, 4 negative. Yeah. Okay, no problem. Let's see. So now that I think we have a clear picture of what we're looking at, right now we want to go back to our our checkpoint problem. And we want to go back here, and again, I like doing it this way with just the electron, right? If it's just the electron, this will only be negative charge, right? So at point S, the field line will be a little small, and at point P, it will actually be bigger because it's closer. Not that I made them noticeably bigger or smaller than each other, but I hope you get the idea. And now I want to know what is the direction at point R and C of the direction of the net electric field. Well, this could actually be an interesting question. So now we'll actually write right on here. So at point S, we have a small field going towards the electron, and we have an even smaller field pointing out away. And how do I know it's smaller? Because the proton is, by definition, much farther away, right? So, and they have the same charge, the same K is involved, but we know that this distance is bigger. So because, keep in mind that E is equal to K Q over R squared. Okay? So when you look at both of these, Q is the same for both of them, and so is K, but the R's are different, and it's in the denominator, and it's squared, right? So you're going to have a much lower impact here on S from the proton than the electron. So the net field, that is, EP EE plus EP, hold on, that will be towards the right. Yeah? And then when we look at the at point R, when we look at point R, what V is, I don't know where I wrote a V. Oh, V, that's Q. That's not a V. That's a bad, yeah, that's a Q. Oh, I can't erase. I wish I had a better eraser, but I don't. I can only erase everything. Yeah, so I'm going to write that again, though, because that was pretty terrible. F. Okay. Q. That's an R squared. It's not a V. So. Oh, can I? I think I have to do this. I think I have to do the selector key. Yeah. No, it's true. I can move some things around, but it's, you know, it's a pain. Now it's been ruined. So I have a much cheaper stylus. I get the feeling I did not go all in on the stylus. But let's finish the checkpoint. So here in R, right, we're in the same in a bit the same predicament. The field will be coming again. We're going to be, the field line will go towards here. But you'll notice the field line will add here, right? So even no matter what it is, the field lines both point in the same direction because it goes from the proton to the electron, right? So each charge starts to add here at R. So it's clearly going to the left. Or from R is going to the right. I did it backwards. And at point R, we're going to the left. I hope you can see that. Okay, any questions on that? Try and work that one out on yourself. Play around with the field lines and make sure you get it. So why don't you do that for a couple minutes and ask me any questions you have as you're doing it. Okay, so can you do the example? Do an example with values. For electric field, the lines will point to the left and right. I think I have an example with values. Let me look at it first. I'll make something up if we don't. But yeah, because I think my example does not have values, and that might be particularly infuriating if that's what you're looking for. So let me check on that example. Okay, yeah, no, it doesn't. It has a few numbers, but not really. Well, actually, it sort of has numbers. We'll take a look and see if it'll work. If you want something with numbers, I'd say you can put your own in, and you'll see how it works at the end. But the next slide is an example slide. Yeah, no, I hear you, Carl. So if we'll go through my example, and if you still want something with numbers in it, we'll modify that, and if not, we can do another one with numbers. No problem. Okay. Right now the numbers are actually can be a bit of a crutch, right? Because you get a number and you can compare the number, but really the key here is to see how the field is behaving, right? Which direction it's going. That's why, even though it can be frustrating, it can seem a little abstract. And the next thing I have set up is an example. So we are in no way leaving this particular problem at the moment. We're just going to expand the checkpoint. So let's do that. I think we're ready to do that. Oh, wait a minute. What is it? It says the blue. Right. Are they going to the left? So at point, I'll delete it and sort of redo it. Hold on. So remember here at point S, right, for the net field, you want to look at this and go, okay, there's a field going towards E, right? And then there's a field from the proton, and I'll draw it here, S, going away. And again, we can use Coulomb's law to infer that this is small. Not only is this smaller, but this is bigger, and that the overall net direction will be towards the positive x direction, right? So that's for point S. This is part D. Yeah? Now for R, I'm going to do it a different color because it can, and it's awesome. For R, right, which is right here, you'll notice the field for E, it's coming, again, it's going toward it. But for P, it's also going towards the electron as well, in the same direction. So these, the two red arrows will add to make a bigger arrow, and that must necessarily point to the left, or in the negative x direction. All right? And again, that's what we're really after here, is which way are these fields behaving? Because once you have the numbers, as I think you'll see, we can just plug it in. But like I said, if not, well, I'll set it up and show them what some numbers look like. Can I summarize A and B again? Oh, well, A, yeah, I could. I don't want, I will. So A is the same, A and B are the simpler versions, right? So when we do that, when we're doing that in A, we just look at the situation where there's only an electron, right? We completely ignore the proton. Okay, so due to the electron, we just find the field here at R, which will be like that, and the field at S, which is farther away, which will be smaller. And by, yeah, this one should be bigger. Okay, yeah, so you see it. Yes, yes, that is what I meant by EE. The electric field for the electron plus the electric field for the proton. Yeah, very good, Seda. Yeah, they're both moving to the right. Exactly, they're both moving to the right. Well, here they're both moving to the left. At least my left, when I look at it. So, but yeah, you got the general idea. Okay. Well, both of these are static, right? We're looking at test charges. A test charge, the electric field from, at this point, from both charges, let me go back to my pointer. The electric field from here is due to both of these charges, right? So if you put a test charge, it would just go whoop, right along that field. Here, it would go forward, or it would go basically in the negative x direction. At point S, though, right here, it would get a little bit of push in the negative x direction, but most of that would be in the positive direction. All right, that's for B and D. If we're looking here only at E, then yeah, on the right, you're going towards the electron, and you're also going towards the electron at S. So either way, it's towards the electron for A and B. Yeah. Okay? All right. Okay, I want to get through this example, which was sort of where I thought we might get through today. I'm glad we got here, but I want to be sure we have numbers in case, because I think Carl brings up a good point. We want to see some numbers. And this is because point S, right, point S is further from the proton. So if you look at Coulomb's law, or not Coulomb's law, but I had a professor who used to call it Coulomb's law. It confused the hell out of me when he'd write for the electric field. I will not do that to you. When we use the definition derived from Coulomb's law, let's just write it down again. Always good to write. You can see explicitly, let me change my color. You can see explicitly where that distance term comes in, right? Right here. So we can see from there whether it'll be bigger bigger or smaller? Yeah? Okay. So, no problem. So let's get to our example. Now, I don't know that, so Carl, I will let you be the arbiter of if these are indeed numbers. If you want to throw something at me, I'd kind of understand, though. Because as you can see, the numbers here are still in terms of Q. But let me tell you this. If it would be easier for you, you can do, I won't use the number immediately, but it is totally okay to say, well, let's say that Q is equal to, oh, hold on. If you think it'd be more clear, you could definitely say let Q equal, and you could just make up a number here. Let's say 10 nanocoulombs. That's completely fine. It'll put numbers everywhere, and you can see how the numbers start to go. Be careful. This goes for everyone. We're at the point where you got to be really careful when you're calculating stuff. Okay? You'll notice that you're often going to get numbers with nanocoulombs, so you'll have stuff in it with 10 to the 9th, multiplying by 10 to the minus 9th, right? And then God knows what distances you'll have. It could be micrometers to light years. It could be anything. You really have to be careful with your calculations. In fact, my recommendation is if you're doing homework, actually on a test too even, is if you have a weird scientific notation number, right? Let's just make somewhat like 6 times 10 to the 5th times 3.28 times 10 to the minus 9. What I would do is I would take these parts, the 10 to the 6th and the 10 to the minus 9, and I'd evaluate that by hand. Minus 9 times 10 to the 6th, that should be trivial. And then do this part in your calculator. Or just be awesome and know it's going to be about 20. Calculator. And then you get your number here and your exponent here by hand. You don't have to worry about it much. That's a little trick I do to not go crazy with exponents. So hopefully that helps. But let's sort of talk and see this problem through. So we have these two charges here. You'll notice we have Q1. I'm going to go back. Here we have Q1, Q2, and Q3. Now, we have values for the charge. So the charge value I just made up here, but you can say Q1 is equal to 2Q. Oh, now I'm hearing stuff. That's not good. Hold on. Okay, I'm not hearing myself now, so I think someone turned on their microphone and I could hear myself through the microphone. Not cool, everybody. That was awful. You have to suffer through me. I just get to hear me through my own voice. So we have our Q1, Q2, and Q3, and notice the values here: plus 2Q, minus 2Q, and minus 4Q. Okay? They're each at a distance d from the origin. So you notice you have the same d, and they're nice enough to give you these angles. So the question is, what is the electric field at the origin? Now, the way to do this problem is to break it up into smaller, easy problems and do them one at a time. Okay? So you'll notice the first thing I want to do is sort of get a feel for the direction of how this is going to go. Now, at the origin, here, right, I'm going to go to pencil mode. Is Q1 positive or negative? That's the first question I want to ask. I look at my problem and I can see it's positive. So the question then becomes, no. The question then becomes, where does my charge go? It starts on positives and goes away, right? So I want to draw that line there. Now, for Q2, which you'll notice is on the same sort of straight line, I can ask, is Q2 positive or negative? Notice it's negative, so you have another line that goes like this. And that just comes from the nature of each one of these. This one is due to Q1. This line is due to Q2. Okay? And again, field lines start at positives, and that will have this field line go through the origin that way. And Q2 similarly, we'll have it go through the exact same way in the exact same direction. And of course, we'll have E1, we'll have our first, we'll look at E1 plus E2. Hold on, let me, I'm going to try the selecting tool and delete these. All right, that was helpful. So we have E1 plus E2 is what we're going to want to look at, right? We know the direction of that will be this 30 degrees below the x-axis because they just line up. They're on that line of sight. But in order to add them together now, we have K, right? Q1 is going to be 2Q over D squared. And if you look back, you will notice I want to make sure, yes, you will notice that, and I haven't been writing it very often, but that if you go back to the beginning of the chapter, they will write that in general, E is equal to KQ, or K times the absolute value of Q. And we do this absolute value because we do the direction later, right? We use our criteria of where electric field lines start and where electric field lines end to figure out whether it's positive or negative. So if we don't do the absolute value sign, it's very easy to double up our negatives or forget them altogether. So over R squared. So that's particularly why we have this absolute value sign here, okay? So what that means, though, is that that's going to be E1, E2 is going to be equal to K. Also, the absolute value of Q2 is 2Q as well. And again, that's a distance D squared. So when we do this, we just add E1 plus E2. Equals 2, or no, that was wrong of me. It's going to equal 4 KQ over D squared. Okay? All you do is add these two together All you do is add these two together directly, and 2 plus 2 is 4. Everything else factors, and that's what gives you this expression. All right? So now we can see this a little cleaner on the next slide, where we will also see what to do next. All right? So now once we have E1 plus E2, which we already said, let's rewrite that from before. All right, I'm gonna select the pencil. E1 plus E2 equals 4KQ over D squared. Yeah? All right. So now we have that, but now we want to find the net field. So we have E1 plus E2 and E3. And we'll notice something interesting here. E3, right, is equal to 4 KQ over D squared as well. So that's rather interesting, right? However, you want to notice something here. It's not as simple as just adding them together again. The reason we were able to, and this is crucially important, the reason we were able to add directly in a very easy way is notice here, E1 and E2 separately. They're the same length and they point the exact same direction. Okay? Very different from E3. E3 and E1 plus E2 do not point in the same direction. Right? Now, if you want to argue from symmetry here, you can and we will. You'll notice that they're both 30 degrees above and below the x-axis respectively here. And what we can do is we can say, all right, the y component part, right, the vertical components are going to cancel, and our only remaining part for E total will be right along the x-axis. Okay, like that. And we know that that's going to be E total. I'll call it 1, 2, 3. That helps. And that total E will be along that way. So we've got the direction. It'll be to the right, you know, positive x. Now we have to find the magnitude. But in order to do that, you'll notice we're not adding all of the vectors together. Or we'll notice that the magnitudes are the same. But we'll notice that we first, in order to get E total, no, they don't subtract. That's a good point. They actually, Jesus, that's a really good point, and I want to reiterate it. If you look here, I always got to click this. In the y direction, they do subtract, right? And they subtract evenly. So we know that E3y minus E1 plus E2y is going to be 0. Okay? But they add in the x direction. So we can say that E3 or E total equals E total x equals 2 times E3 in the x direction. Because we already see that E3, the magnitudes of E3 and E1 plus E2 are the same, right? So we just double it up and say it's 2 times one of them. And but we also have to look at that and say, get rid of that x component, or to take it explicitly, and we have to say that equals 2 E3 cosine theta. Okay? And that's going to equal 8 Q over d squared times cosine of 30 degrees. Now, if you want to get numbers to see what this might look like, let's use Q equals 10 nanocoulombs, like before. And let's do D equals, I don't know, let's say 1 centimeter. And from there, you should be able to plug that in and kind of get something. But all you do is check that number from one to the next. Okay? So I'm going to leave it open for any questions. That's pretty much what I have for tonight. And I think it went well as far as getting to where I wanted to go. I do wish I could be in the class with you all, talking to you. But, you know, pandemic times call for pandemic measures. So anyway, again, the labs, just so you're kind of clear on that, the labs will be, so the answer is at the bottom corner, right? Yes, the answer is at the bottom corner. Yeah. And you can plug those numbers in and see if you get something. I'll stick around for a little bit after the class to answer questions. Carl, are you okay with the numbers? I can come up with something, and we could start there next week if we want, because we're just kind of running out of time. But let me know if that works, or if you want something else, if that helps. We can do next week. Okay. I'll find something good. You know what I'll do? I'll pick a really easy homework type problem next week, and we'll start there to review this stuff and to get going, and then that'll be all numbers. Okay. I think that'll be good. But for lab, keep in mind we're kind of gonna shorten the number of reports. I think you're gonna want to write your report for speed of sound, like your short form report. That's fine. And then my Skype is Poland at lagcc.cuny.edu. I'm sending out my Skype address again, so I just want to be sure I spelled my name right. Yeah, turn that in next Wednesday. Yeah, let's not beat ourselves in the head. I sort of interpreted instruction, meaning I couldn't ask you to do anything. What are the subscripts for E values in the next equation? Which, you mean here? What are the subscripts for E values in the next of the long equation? Wait, I don't know which one you're talking about. Oh, in the long equation? Oh, I got you. So here we have, this is E total x in the x direction. This is E3 in the x direction multiplied by 2, because you'll notice they're the same. And then this is E3, 2 times the magnitude of E3, which is right here, times cosine of theta. Okay, yeah. Sorry, fresh terms 12. Right. I'll do it again. So this is E total, ET total in the x direction, because we noticed the y direction canceled by symmetry. And then in the x direction, it's I have in exchanged recognized that E total is just 2E3, so that's 2E3x, right? And then from there I took the x component, so that's 2 times E3 times cosine theta, and then yeah, that should work. But I want to finish talking about the labs first. If you follow what I wrote, I just don't want this to kick us out, so I'm going to stop the recording. So we're going to stop.